So this is the packet from Friday that we started on Friday, and we're going to finish this up. It should help you with CP19, which you picked up today. And so we've done all but the last problem. So we're on the back of that packet from Friday. All right, a weight is attached to the end of a very long spring, which is oscillating up and down. So it's a very long spring. We're talking about something long enough to be hung from this ceiling, which is quite high. So it's a very long spring. And it's oscillating up and down. So oscillating is just moving up and down. As it bounces, its distance from the floor varies sinusoidally with time. So again, sinusoidally just means that it is, if we compare it to time, the height versus time, it's going to be up and down like a sine or cosine curve. Either function works. When your stopwatch reads 2.5 seconds, the weight reaches a height of 40 centimeters above the floor. At 3.75 seconds, it reaches a height of 12 centimeters above the floor. Make a sketch of the function. So what we want to do is we have time on our independent axis, and here we want the height above the floor. The height above the floor on our vertical axis. And so we have some information. So it says when my stopwatch reads 2.5 seconds, the weight reaches a height of 40 centimeters above the floor. Well, that's the order pair. Now, I don't know. I mean, normally we'd start time at 0, but the only information I have is right here at 2.5 seconds. I'm just going to mark it, and that's what it is. At 2.5 seconds, how high is our spring, the weight of the spring? It's 40 centimeters. So it's right up here at 40, and this is in centimeters. So I'm going to put a point there. 2.5 seconds, we're 40 centimeters above the ground, above the floor. At 3.75 seconds, it reaches a height of 12 centimeters above the floor. So I'm just going to mark this 3.75, and it's now 12 centimeters above the floor. So that would be the minimum. So if I have the maximum and I have a minimum, when will the weight be 40 centimeters above the floor again?
I'm guessing 4.25.
4.25. How'd you get 4.25?
Just a guess.
Just a guess.
Oh, wait.
Okay, I like your thinking. So you're saying subtract these two because it took how long to get to the minimum? 1.25.
Yeah, but from,
Okay.
yeah, but from 0 to 2.5 would be 2.5. So
I know nothing before 2.5. I know nothing before 2.5. Okay? So I can't use anything before that because I don't know anything about it. Oh, okay. So you're saying that the time it takes to go from the high value to the low value should be the same as from low to high. Does that make sense to you?
Yeah.
Okay. So then if we put on another 1.25 seconds, then that's going to put me at 5 seconds. Okay, so 5 seconds. And we just made one beautiful little cosine curve. One period of a cosine function, right? Okay. So we want to graph this function over 2 periods. So when is it going to get to the low point again? 6.25, and we got that by, again, adding the 1.25. Okay, and then when's it going to be to a high point again? 7.5. Good. And so there is 2 periods of this cosine curve. And again, you'll notice I did not make this go all the way to the axis because I know nothing about where it was at time 0. I only know what they gave me, which was at 2.5, it's at 40. Okay? So yes, it goes on, but I don't know where it intersects. Okay. If you can do that, ladies and gentlemen, then that's everything you need to be able to do to write the cosine equation. All right, so this is a great picture, and now we want to write the model. So the first thing we're going to do is figure out D. How do we find D, the vertical shift? Half of low plus high. Very good. Our lowest value is 12, and our highest value is 40. So half of that would be? What? 26. Okay, 26. Good. All right, so 26 fits right about in here, and that's good just to sort of say, hey, yeah, that seems about even. So how do we figure out the amplitude? High to the midline. High minus D. High minus the midline. So that'd be 40 minus 26 is 14. Good. So is this a positive A value or a negative A value? How do we know that it's positive? Yeah, because it's high, middle, low, middle, high. So we know it's a regular cosine curve. All right, ladies and gentlemen, what is the period of this function?
2 pi over period.
Well, that's B. So what's period?
What is the period? B times something.
2 pi over B.
What does period
B
mean?
times D.
Wait, you guys are answering the wrong question. What does period mean? The time it takes to repeat itself. So from starting point to complete one cycle, we want to know how long it takes to go from here to here. 5 minus 2.5, which would be 2.5 seconds. And again, that's 1.25 and 1.25. It's two of those. However, you need to think about that. Now, the question you were answering was, how do you find B? 2 pi over the period, which would be 2 pi divided by 2.5. Normally, I'd say don't ever leave a decimal inside of a fraction, but I'm going to break my rule because the point is to write the equation, and that's what we want to do. Then, how do we figure out the whole bx, the c thing? C equals b times x, and x is that starting x value. And so we know b, which was 2 pi divided by 2.5. And what was our x starting value? 2.5. So again, our starting x, that's our starting x value was 2.5. And so what happens? Yeah, hey, handy. Okay. Another reason why I didn't want to reduce that. Okay. So then that's everything we need, and we can plug it into our model. So y equals a, which is 14, times the cosine of bx. So I'm going to write 2 pi x over 2.5. bx minus c plus d. And of course, what you really want to do then, because you're writing equations, you have a function, you can check it. Okay? You absolutely want to be able to check these things, because if I was going to ask you something like this on a test day, I'd give you a picture and a lot of different equations. And, you know, one thing you could do is just type in all the equations and see if they work. So you definitely want to know how to check. All right, so I'm going to type in here 14 cosine of 2 pi x divided by 2.5 minus 2 pi plus 26. I'm also going to set my window so that it looks like the picture we've drawn, because that is the easiest thing to do. I'm going to start at 0 and end at 7.5. I'm counting by 2.5-ish. And I can start at 0 and end at like 40-ish. And there's our oscillating weight bouncing up and down for a small period of time. And I want to check some of these. It looks a little bit different, but I want to check maybe this point. So I'm going to use trace at 3.75. And there it is, at 12. So I checked that point, even though my graph looks a little different. It's pretty good. Why does my graph look different?
Because it shows
Because it shows the stuff before 2. So if I just did from 2 to 7.5, then you'd see, oh, and it was even 2.5, not 2. So there's from 2.5 on. All right, very good. Do you have questions on that one? Good, you have 2 more just like that. And so we're going to switch to the next thing. So don't lose that. You do not have to turn this in. This is notes, really useful notes, especially because this one is your regression project. All right, so make sure you have that stuff. We're going to go to the one on the table, which is CP19. And we're going to do this one. This is really cool. So open it up. We're going to do number 6. You guys need to do 1 through 5. We're going to do this one together. Number 6. Does anyone in here right now have a Casio? Okay. All right, just checking. It's pretty good. This is the one thing I found that is lacking, but it'll work for the most part. It's not quite as cool as it is on the TI. So you're going to want your calculators out, ladies and gentlemen. Here we go. The swinging pendulum. A ball is suspended by a piece of string above the floor. The ball swings side to side as if it were a pendulum and maintains a periodic motion for a small length of time. Eventually, what would happen to that pendulum if it was just a ball that you released? Eventually, it would stop, right? Okay, that's called a damp trick function. So gravity is actually dampening the motion. All right. But we're going to pretend that for a small length of time, this pendulum is going to be sinusoidal for a little while anyway. While the ball is swinging with this periodic motion, students were able to take the following information. The height of the ball above the ground at its equilibrium point was 0.33 feet. So here is, you can see on the picture here, the equilibrium point. That's where the ball was just hanging straight down. And we want to label some ordered pairs there. What would the label for that equilibrium point be? 0.33, because it was 0.33 feet above the ground and 0 left to right. So that makes sense. Okay, good. The height of the ball at its highest point was 1.7 feet. So this ball, as it swings out, it gets a little bit higher, and at its highest point, it's 1.7 feet high. The horizontal distance from the equilibrium point to the highest position was 2.26. That's kind of tricky, but that is the horizontal distance. So as this ball is moving to the right or to the left, it's moving to the right, and it gives 2.26 feet to the right or to the left. The length of the time for 5 complete swing cycles was 4.8 seconds. A swing cycle is completed when the ball returns to the same position like the equilibrium point and is headed in the same direction. I hate typos. It's really driving me nuts. Okay. We want to go ahead and label the rest of these ordered pairs. The x-axis represents the horizontal position of the ball from the equilibrium point, and the y-axis represents the vertical height or position of the ball above the ground. So this right maxima over here would have what ordered pair? 1.7. Very good. 2.26 feet horizontally, 1.7 feet vertically. What would the left maxima be? Good. Negative 2.26 units to the left and 1.7 feet above the ground. Okay, very, very good. These are really good data points. And what we're going to do is model the position, the horizontal position at any time t. So we have time on the horizontal axis here, but we're actually modeling horizontal distance vertically, which is kind of a weird thing to do. Okay, so let's see here. It says, think about one full swing cycle of the ball. Equilibrium, move right, equilibrium, move left, and back to equilibrium. So that's one complete cycle. Using the data above, how long will it take for the ball to complete only one swing cycle? How'd you get 0.96? So you divided 4.8 seconds divided by 5 swings. Yeah, and so that would be 0.96 seconds per one swing. Okay. All right. So with that being the case, we're going to say that we started at time 0 and it completes one full swing cycle at 0.96 seconds. So just like we were graphing before, we're going to subdivide that. What's halfway between 0 and 0.96? 0.48. What's halfway between 0 and 0.48? 0.24. And between 48 and 96?
0.38. No, 0.48.
0.72. Close there, Nick. All right, so here is seconds. Okay, 0.96 seconds. So this is all the time points. And at time is 0, our little pendulum is right here at the equilibrium. What is its horizontal distance when time is 0? 0. And then it moves to the right. Where is its horizontal position? 2.26 units to the right. I know that's weird. And then it moves back where? Back to 0, back to equilibrium. And then it moves to the left. Where do we go to the left? Negative 2.26. Weird, I know. And then it goes back to equilibrium. And so you can see here that this motion is what kind of curve? A sine curve. Very good. And since it's a sine curve, we can find out the equation pretty easily. What is the vertical shift of this? 0, centered. What is the amplitude? 2.26. And then I asked, what's the period? 0.96, but we don't use period in our equation. We use B. So what's B? 2 pi over. You didn't know that poi was the plural of pi.
It is.
No. Okay. Again, normally I'd say we don't want to leave a decimal inside of a fraction, but we're going to go with it because it's easier. So amplitude is 2.26. What kind of curve is this? Sine curve. And then bx. So it's going to be 2 pi. Oh, and this is in terms of t. 2 pi t divided by 0.96. It starts at 0, so I don't need a c value, and then plus 0 for the vertical shift. So you'll see this is the horizontal position in terms of t time. So we're using t instead of an x. And I would say we want to check this using our calculator, but I'm going to say forget it. It's right. It's right.
You guys have that.
Okay, let's turn the page. All right, model the vertical position at any time t. So again, we have time on our axis. And now we're modeling the vertical position above the ground, the vertical position of the ball at any time t. Think about the height of the ball. How high is the ball for one full swing cycle? And again, that's going from equilibrium to the height at the right maxima, equilibrium, height at the left maxima, and back to equilibrium. So we want to graph that cycle again. So again, that time is the same for now, with 0.96. And subdivide, halfway was 0.48, 0.24, and 0.72. So same 5 interesting points here. So when time is 0, what's the equilibrium height of the ball? 0.33. And then it moves to the right. How high is it on the right maxima? What is it? 1.7. Okay. I heard something very different. Okay. So then it moves to the highest point, which was 1.7. And then it moves where? Back to equilibrium height, which was at 0.33. And then it moves to the left. How high is it on the left point? Back to 1.7. And then back to equilibrium height. Oh, what happened? Was that 1 period now or 2?
2.
2 periods. Interesting. Interesting. Okay. Vertical shift. How do we find the vertical shift? Oop. Halfway between high plus low. Okay, low plus high. Yeah. So 0.33 plus 1.7 divided by 2 gives me 1.015. And that's about right here if you were interested in that sort of thing, but 1.015. What's the amplitude? Almost. 0.685. How did we get 0.685?
I subtract 0.33 from the number I just got.
Yes. Yeah. 1.7 minus 1.015 will give us that 0.685. High minus the d value. All right, period. What is the period of this graph? 0.48. Very good. Which, that's an 8. And so what's b going to be? Good. 2 pi over 0.48. So is this a cosine or a sine curve? Cosine, very easily here because it starts at 0. We want to use that cosine curve. Is this a positive cosine curve or a negative cosine curve? Negative. Yeah, since it's starting low. So I'm going to say negative a there, 0.685. Cosine of b, 2 pi t divided by 0.48. There's still no horizontal c value, so we don't need to worry about that. And then plus 1.015. Okay, cool. Now here's the really cool part. You are going to watch the motion of the ball. So, I know, this is totally cool. So what we just did was we wrote one equation that gives the horizontal position of the ball and another equation that gives the vertical position of the ball, all in terms of time. And what we can do then is do what's called a parametric mode. There's a pair of equations, and those two equations together give you an ordered pair, x and y, all in terms of time. So we can actually watch this motion in terms of time. It's very cool. So first, we're going to put your calculator into parametric mode. So for the TI, you're going to go to mode. And you see function and par and pole and seek. We want par. Par is parametric. Right there, just highlight it. On the Casio, you're going to go to your graphing menu and, Oops, dang it. Sorry, I got to delete these. Okay, you're in your regular y equals. You can go to type and parametric. It's not Parmesan cheese, it's parametric. And so what happens in parametric mode, so ti go to y equals. And what you see here is we have an x1t and a y1t. So that's your horizontal equation in terms of time and your vertical y value equation in terms of time. And we're going to type in, enter your x of t equation into x1t and your y of t equation into y1t. So for both of these, we're going to type in, so first you're going to type in 2.26 sine of 2 pi. Again, use your alpha key, not the alpha, but the key right next to your alpha button. That's going to give you the right variable. It's really important that you use the right variable. 2 pi t divided by 0.96. 2.26 sine of 2 pi t divided by 0.96. Okay? It should be your x of t equation, 0.96. Yes. B T. All right, and then you're going to put the y of t equation, so this equation, into the y1t equation there. So negative 0.685 cosine of 2 pi t divided by 0.48 plus 1.015. 2 pi t divided by 0.48 plus 1.015.
We have to make it a circle on the.
Yeah, hold up. I'm not there yet. Okay. Is anyone not with me yet? It won't matter if it's here for you. Let me see how you got it. 5.96. That should be fine. Okay, all right. Then we are going to change the style of your graph to the ball option. So for the TI, there's these little lines right here to the left of X1. And so you're going to move your cursor over there so you can see it starts blinking. And right now that's drawing a line. And if you just hit enter, it draws a thick line, or it draws this weird like goofy glasses line. And then there's ball option right there, which looks just like a circle. And then you're just going to arrow off of that, and that's going to graph the ball option. On the Casio, we don't have something quite like it, but it's style. So if you go to style, and the best option is really just to do the small dots. Oh, so you got to move your cursor up to this little line. It's telling you it's, oh no.
It only does.
Oh no.
Something for it to go get.
Okay, so you highlight that, and then you can change the style to the little dots, and you can see that that's. Oh, see. Okay. Yeah. So you arrow your cursor back to the little, to the right or to the left, and then just hit enter until you see just the circle. Oh, yours. Yeah. You have to do a font. So arrow right there. See line. Arrow down. And there you go. Nope. There it is. All right. All right. Yeah. If you have a newer. Hi.
Is there room number for
335.
this?
Okay. All right.